At this point, I want to switch to a new notation. The new notation for IIR filters hasn't changed at all. It's going to be the sum up to capital M of these different coefficients divided by the sum up to capital N of these coefficients. So this is the exact same as we've talked about. And this is an order N filter. And just as an example, so here's an example of an IIR filter. And you know it's IIR because its denominator is not equal to 1. So it's got to have a bunch of poles off the origin. And who haven't I called on before? Nick, did I call on you?
Yes, sir.
I have? Then I think I've called on, oh, Garrett, you've been hiding out there. So what is this filter's N? What's its order?
EE2.
Yeah, exactly. It's an order 2. Biggest root of the denominator. Biggest order of the denominator, biggest power. Now, an FIR filter, this is where we're going to use a slightly different notation. Up until now, we've been saying, well, the denominator is 1, and we write this from k equals 0 to m. Now we're going to write it from 0 to n. Everything else stays the same. So it's going to be order. When we talk about a 10th order FIR filter, we're not talking about the denominator. We know the denominator is always going to be 1, which means it technically has an order of 0. But that's not a useful way of talking about FIR filters. So we're going to say now the n is in the numerator, and an order n means that it has n zeros to it. So as an example of that, 1 plus z to the minus 1, I'm going to make it like this, plus z to the minus 2. And you can see that this is an FIR because it has only a length 3 impulse response. And you can see that it's linear phase. I'll write this down. FIR, since the length of h of n equals 3. And you can see it's linear phase since h of n is shifted even. It's 1, 1/2, 1, but it's been shifted. If it was here, it would be 0 phase, and it's been delayed by 1, so it's going to be linear phase.